We looked at vectors in the previous video. In this video, we will see what kind of operators we can apply on these vectors. When we talk about operators, we generally mean linear operators. So let me first define what linear operator is. In this, we will mostly concern ourselves with vector spaces. So let's say there are two vector spaces, V dimension n and W dimension m. Then a linear operator m from V to W is an operator which satisfies these two conditions. One is that the action of m on x plus y should be m of x plus m of y. So here addition is happening in vector space V, here addition is happening in vector space W. On the other hand, if I have a scalar alpha, then the action of m on alpha x is same as alpha m of x. Here the scalar multiplication is happening in V, and here the scalar multiplication is happening in W. If these two conditions are satisfied by an operator, then m is called a linear operator. But let's see what we can say about these linear operators m. First thing to notice is that the zero vector of V will get mapped to zero vector of W. You can take it as a small exercise and convince yourself that this is indeed true. Also, by the two properties listed above, if I keep applying them, then m on a vector like this can simply be written as this. Remember that this is how we write any vector V element of. If x1 to xn was a basis, then it is enough to know mx1 up to mxn, and we would know the action of m on complete vector space V. I want to re-emphasize this. It's a very important point. Because of equation 1 as done above, you notice that if x1 to xn was a basis, it is enough to know how m acts on the basis. If I know what is the value of m of x1, m of x2, m of xn and so on, then give me any vector in the vector space V. If it is represented as alpha 1 x1, alpha 2 x2 up to alpha n xn, we know that any vector can be written like this. Then action of m is given by equation 1. To say it concisely, to give an action of m, I just need to specify its action on the basis. This is a very important characteristic of linear operators and will be very helpful to us. We can also define addition on linear operators. We can say that if we have two linear operators m and n, then m plus n of u is m of u plus m of u. Simple addition of two operators. Also, I can define scalar multiplication of linear operators. So alpha m of u is alpha m of u. This actually shows that the set of all linear operators in itself is a vector space. Last time we saw that we can define vector space over reals, we can define vector space over complex numbers. Here, even the set of all linear operators over a vector space is itself a vector space. If you haven't done it till now, you should go back and see what a vector space formally is. This vector space, the set of all linear operators from V to W, is denoted by LVW. Remember, it is a vector space. In case you're talking about LVV, it is generally denoted just by LV. So this is a shorthand for writing LV. Now, I will tell you that these linear operators are nothing new. You have seen them all your life. So let's talk about matrices. I am sure you know what matrices are. Suppose, again, V has dimension n and W has dimension m. So you remember that if I take a matrix M, which is M cross n, then you can easily show that the action of matrix M is actually a linear operator on the vector space. Your M is like this. It has m rows and n columns. You pick a vector in V, you multiply, you will get a vector which has m coordinates, which can be thought of as a vector in W. So M is an operator from V to W. It is easy to verify that M is actually a linear operator. That is good. We know now that matrices are linear operators. What about the converse? Can we write every linear operator as a matrix? That would be very nice, because you already know a lot about matrices. It turns out that this is also true, and proving this is not very difficult. Let F be a linear operator, again from V to W. In this case, I will first choose a basis of V. I can say it is V1 to Vn. Similarly, I will choose a basis of W. Let's say W1 to Wn. I know that f of V1 will give me some Z1, f of V2 will give me some Z2, f of Vn will give me some Zn. Remember, Z1 to Zn are elements of W. So I can write Z1 as some linear combination of these vectors W1 to Wn, because they lie in this vector space W. And now you might already see a matrix forming. My claim is that if you just rearrange these beta ij's, you will find the matrix MF whose action on V to W is same as action of F on V to W. Again, you should do this manipulation and convince yourself that this is the case. What happened here? It turned out that I can take a linear operator and come up with a matrix representation for it. That's good. Remember, we have to talk about Dirac notation also. So let me just talk about Dirac notation. First, we last time saw that the inner product of two vectors was written like this. This was equivalent in the vector notation to this quantity. I can also write something which is called an outer product. So this should mean vector notation as phi psi star, and you can notice that this is a matrix. In other words, this is a linear operator. What is its action? It takes psi to, or any vector v, to v psi times phi. This is the action on any vector v. This is the matrix. Similarly, you can define actually any linear operator. So if a linear operator takes v1 to vn to z1 to zn, then you can convince yourself, or you should convince yourself, that if m takes v1 to vn to z1 to zn, then m is summation over I zi. Actually, that is not true. I have to say it is zi vi. So you should show that m is the matrix representation, or this summation I equal to 1 to n vi is the matrix representation of the linear operator which takes v1 to z1, v2 to z2, vn to zn. Assume that v1 to vn is an orthonormal basis. And then you can easily prove this. We have seen that linear operators can be converted into matrices, and matrices are linear operators. But the conversion of linear operators went through standard basis. Is that necessary? Actually, the equivalence does not depend upon the choice of basis. What do I mean to say here? I want to say that you can pick any choice of basis and still this equivalence will work. So let's pick basis. So let's say that V has basis V1 to Vn, W has basis W1 to Wn. Then you just figure out what is MV1 to MVN and write them in terms of W1 to W1, and that will give you a matrix representation of linear operator. So we will keep this thing in mind, which is that a matrix is a linear operator. That is good. And a linear operator, given a choice of basis for both V and W, turns into a matrix. And this is how the equivalence between matrices and linear operators work. We can write out the action of this matrix in ket notation very easily. So this is same as MV. This is on the right hand side I have the vector notation, and on the left hand side I have the Dirac notation. I can talk about inner product of U with vector MV. This turns out to be equal to M star U. Let me write it cleanly. V, and there is a shorthand for it. We denote it by UMV, showing that you can keep M on either side. You can apply M on V and then take the product with U, or you can apply M star on U and then take the product with V. This notation is going to be very, very helpful. To take examples of some standard matrices, the easiest matrix would be zero matrix, which is all zeros. Then there is obviously identity. You are again familiar with it. Another important matrix is J, which is all ones, where I put 1 in every position of the matrix. This will not be the identity. So make sure that you understand the difference between identity matrix and J matrix. Once you have looked at matrices, you must already be familiar with kernel, image, and rank. They are given in notes also. I will briefly describe them. Remember, kernel of a matrix M or a linear operator M is the set of vectors V such that MV is 0. Remember, M is a linear operator from V to W, vector space V to vector space W. Similarly, I can define image of M. This is the set of all vectors W such that there exists a V for which MV is equal to W. So kernel tells me all the vectors in the domain which go to 0. Image tells me the set of all vectors in the range which have a pre-image. There should always exist a V such that MV equal to W. That's the image. It turns out both kernel as well as image are vector spaces in themselves. They are subspaces of V and W respectively. We will notice that kernel is a vector space or subspace of V, image is a subspace of W. There is a famous rank nullity theorem which says that rank of M, which is the dimension of image of M plus dimension of kernel of M is equal to N. N is the dimension of V. The proof is given in the lecture notes. You are welcome to look at that. Another important theorem is column rank equal to row rank equal to rank. Remember, column rank is the dimension of the space spanned by columns. And similarly, you have row rank. They turn out to be equal. The easiest way to see it is probably Gaussian elimination. And column rank equal to rank is not difficult. That is something which you can convince yourself. This is all the information we will need about matrices and vectors. In the next video, we will see the first postulate, the actual definition of the first postulate, which will describe the state of a quantum system.